Okay, well, as I mentioned before I started the recording, welcome everyone, and I hope everyone is doing well and making it through okay with this transition that we've done for going to online. So what we're going to talk about today is how we use analog to digital converters. And this is a little bit of I'll say a detailed topic, so we're going to spend some time going through the concepts, so hopefully when it's all said and done, you understand how this works. Now, one of the things that we have to keep in mind is we live in an analog world. So you hear me speaking, my voice is at some point digitized on my computer, transmitted, and then you play it back on the speaker to where now your ear hears an analog signal. And so many of the phenomena, many of the systems we control, many of the various attributes that we are interested in are all analog quantities. And so what we'll have when we use these microcontrollers, various kinds of sensors and other devices that we want to be able to extract information from. And so and I lost one of I'm looking for something here. I need to monitor what's going on. So excuse me for, I do it this way. Okay, so eventually we'll get back to where we want to be. So for example, if I have a sensor, I may have some behavior where I'm measuring maybe pressure. And so this would be pressure. And my output of my sensor will be some DC voltage. So this might be, let's say, if I can draw this. So this is 3 volts, and let's say my max pressure is 100 psi. So I would see that I'm going to, if I look at I see this is a relationship I have with my sensor. And now what I want to do is I want to sample this system. So I might want to sample it with a system that has 1,000 or 1024 possible levels. So if I sample and I have 1024 possible values, then if I did some math, I would say that if I'd have 100 divided by 1024, which would give me 0.97, 0.0, and let me fix that. Let me erase that. .097 psi per bit. So my least significant bit would have a resolution of approximately 1/10 of a psi. Now that might be okay, maybe not. So if I had some sort of signal that basically is time varying and I sample it at some interval, I will see that I will have values that correspond to those, and what we'll see is we'll typically represent that as a series of values that will look like this. And hopefully I have some measure of correspondence between them. So one of the things I have to worry about when I'm sampling a signal, so I'll say issues with sampling. And one of them is quantization. Now let's say I wanted to measure 1,000th of a psi, and I have my 1024 possible values. I'd say, well, I have an issue there, and that's what we talk about when we talk about quantization. What is the resolution, the finest resolution
I'm not sure if you can hear me, but you lost your audio, and we're trying to tell you in the chat room.
Okay, are we back with our audio? Okay, so
Yes.
let me just, so when I'm sampling at a, and I'm going to mute this. So when I'm sampling at a, if I have a low frequency signal, looks like my, I'm going to stop this. Okay, so what happens is when I'm actually sampling the signal, and come back to my, so when I'm sampling the signal, depending on the frequency content of my signal, if my frequency content starts getting high enough, then my sampling rate needs to increase as well. And so there is an issue there. It's called the Nyquist sampling rate, or the Nyquist sampling limitation, where I have to sample at least 2 times the highest frequency content of my signal. And that's something that you study in digital signal processing, and we won't get into that in any detail in this class. But one of the things that I need to be concerned about is the frequency content of my signal, and am I going to be sampling fast enough in the event that I am interested in the frequency content of the signal so that I don't distort the signal. And one way where you see that is oftentimes in movies where you see it appears the wheels are going backwards, and that's because frequencies are being distorted. And so the sampling rate is another issue that I need to be concerned about. And so another thing that I need to be concerned about is this notion of jitter. And so I mentioned that I need to sample at some interval, this delta t. So if this is delta t, and this now is delta t plus some epsilon, and a little bit higher epsilon. And so the thing is, what happens is if I have jitter in here, this is going to be problematic if I'm relying on this delta t for some sort of thing like calculating velocities or other sorts of things like that. And so and one of the reasons I'm getting a few comments about the wheels appearing backwards. So I didn't mention that when a camera is taking a video picture, what it's doing is it's taking samples or taking pictures at an interval, maybe 30 seconds, 30 times a second. Your TV's rastering at 60 times a second. And so the thing is I'm not sampling at a fast enough rate to capture either the rotating wheels or rotating propeller, and that's why you have this problem called aliasing that distorts the frequencies and they look like they're incorrect. So when we are converting signals from analog to digital, there are some issues that we need to be concerned about, specifically things like quantization, sampling rate, and the sampling rate gives rise to a problem called aliasing. And that aliasing has to do with distorting frequency. And so the reason that you see the wheels go backwards is in the digital domain, I actually have negative frequency. So that negative frequency would correspond to the wheel looking or appearing as though it's going to rotate backwards. Okay, so what we're going to do is we're going to use a device in our process of determining a digital estimate for this analog signal, and this is our handy dandy op amp. So I'm just going to say here's my plus VSS and here's my minus VSS. This would be plus, minus, and say V in 1, V in 2, and here's V out. So if V in 1 is greater than V in 2, then V out will be equal to plus VSS. And if V in 2 is greater than V in 1, then V out will be equal to minus VSS. So this is an op amp, and many of you probably have learned about op amps as actually amplifiers, and we do use them as amplifiers, and we'll use them as an amplifier a little bit later. And so when we talk about using these op amps, we're going to be talking about using them in one of two modes. One either as an amplifying mode or as a comparator. And in this mode, this is what we would use as a comparator. Now, you probably have seen op amps, and what are some of the characteristics of op amps that make them desirable? So what are some of the characteristics of operational amplifiers that make them desirable for a broad variety of applications?
Infinite input impedance.
Okay, so I'm going to put op amps, and I'm going to abbreviate it. So I'm going to say Zin is equal to infinity. Other characteristics: zero output impedance, so Z out is equal to 0.
No current flow on the input gates.
Well, that has to do with infinite input impedance. Okay, infinite bandwidth. We typically will say A sub V is equal to infinity. Our gain is equal to infinity, or it's very, very high. Okay? And we'll see that because of this, because of our infinite input impedance, we have a phenomena which we'll take advantage of later on called the virtual short across the inputs. Okay, so we have that characteristic. Another thing that we're going to take advantage of is a voltage divider. So in this case, we have V in plus, and here's, I didn't do my ground, and here's V out. And here's R1, here's R2. So V out is equal to V in times R2 over R1 plus R2. Okay? Everybody remembers that from your circuit analysis. Okay, so what we're going to do is we're going to look at a slightly different, so let's assume now that we want to have 4 levels, okay? And I'm going to make these all the same value, R, 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 and R. So this will be equal to V in times R over 4R, or Vn over 4. This will be at this point, and these are all relative to ground, so this is Vn 2R over 4R. So this is Vn over 2. This is equal to Vn 3R over 4R. Of course, the R's cancel. So this is Vn over 2, and this is Vn over 4. Okay, so if I look at this and I want to compare a signal, so here's my V, actually this is VR. Let me change this. So here's VR, and let me fix this. Apologize for the. So here's VR. Oops. The reference. Okay, so I look at my levels, so this is 3/4 of my V reference, V sub R over 2, and V sub R over 4. So my largest error, let's say that my input value is VR over 4 just minus some very, very small value. So a question is, are we making a 1-bit A to D? Okay, so if we have 4 values, how many bits do I need to represent 4 values? 2 bits. Okay, so this would be a 2-bit A to D. But one of the things, so my max error would be equal to VR over 4 minus some slight epsilon. Okay, so it's going to be almost VR over 4. I'm saying one thing, and let me clean that up. So this is going to be V sub R over 4 minus just some slight epsilon. Okay? So there's actually a better strategy, and what we're going to do is we're going to do the following. So this is R over 2. Here's R, 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 and this is R over 2. So now I have the same total resistance. I still have my 4R as my total resistance, but now if I look at this structure, I see that this is now going to be, this voltage here is going to be R over 2. So here's VR, R over 2 times 1 over 4R. So now this is going to be, is equal to VR over 8. And if I do this calculation, this is now V3 VR over 8. This is 5 VR over 8. And this is 7 VR over 8. So now in this case, my max error is going to be V sub R over 8. So what I've done by basically adding one additional resistor is I've basically been able to, and this is going to be minus some epsilon. And so what I can do is I can use a voltage divider to provide me a list of a number of, or give me a number of reference voltages to which I can compare some unknown value. And what I have here is a picture of a flash A to D, and this is typically going to be modified as follows. So I'm going to, this will typically have an additional resistor here, R over 2, and this will be R over 2. And the reason that's done is again to make my error smaller. So what happens is I have this array of resistors and op amps, And notice it's taken me 7 op amps to be able to implement this, plus my 8 3-line priority bit encoder, so that I can actually come up with a estimate. Now notice, how many values does it take me? So I have 7 possible values. Well, I have 8 because 0 is also a value. So notice it took me 7 op amps, and now I have a 3-bit analog to digital converter. And this type of converter is called a direct conversion or a flash A to D. So this is, come back to black. Or flash. And these are called ADC, analog to digital converters. Okay, now these type of A to D converters are used for very high speed kinds of signals. So if I have a signal like a TV signal, a video signal, there are flash A to D converters, and they tend to be very low resolution. So if I needed 6 bits, so 6 bits would be 31 possible values, then I'm going to need 31 op amps to be able to implement it. So you see that if I'm going to have a very fast direct conversion A to D converter, it's going to take me a lot of circuits. And oh, by the way, they also tend to consume a lot of power, get kind of hot, and so you use them very sparingly for applications where you need very, very fast response. And so this is going to be one approach that we might take. However, as we see that this approach is nice for certain applications, for most applications that we're interested in, this is not going to be an effective implementation. A couple reasons. One is power consumption, the other is resolution. So we want to be able to come up or implement a system that is a little bit faster. And so this is where we're going to look at a different type of operation. So let's come back over here to our system, and we see that we have in our system a analog to digital converter. And this analog to digital converter is 10 bits. So if I told you that we were going to do a 10-bit A to D converter with 1023 op amps and a whole, well, 1023, actually 1025 resistors, we'd see that that would be a very, very large in terms of real estate, take a lot of components, use a lot of power. And recall, we want to use these devices maybe in a battery-powered application, and maybe also in a situation where we don't want to have extensive cooling for the circuitry. So we see that we want to use a different approach. So what we're going to do is, again, we use the op amp as our reference, but now what we're going to do is we're going to use a different strategy for developing our reference voltage. So again, if I have the op amp with no feedback, what I have is I'm using it as a comparator, comparing my inputs, an unknown input to a reference. And I want to know, is it larger or smaller? And so what I'm going to do is I'm going to use a slightly different approach. Okay, so I showed you the flash A to D converter. And this would be an approach that we would use for things like video signals, but we're not dealing with video signals. So what we're going to do is conceptually very similar to a scale that you might see. So I have some unknown weight I'm going to put in one of the cups, and what I'm going to do is I'm going to compare it to a set of weights. And notice each one of these weights is twice as big or twice as heavy as the next mass, and these two look to be the same, but the strategy is I'm going to basically compare it to the heaviest, and I'll see, is the unknown larger or lighter than the heaviest. Then I'll go to the next one, and I'll add that or remove it, and I continue on until I get down to the very, very finest weight, my least significant weight, to get a very precise measurement of what is the exact weight of this system. So this is what is known. the process is known as successive approximation. And so the way that it works is as follows. So we have our op-amp here that is basically going to compare. So this is I think I can annotate. No, I can't annotate. Well, this is unknown. I'll try it. Let's see. Nope, that's not what I want. I'll do it on another. So I have my unknown signal coming in on the positive terminal. I have a known signal that is generated by a D to A converter. And so what I need to do is I need to come up with some sort of way to implement an analog signal using binary values. So that the way this system works is I have my unknown, and this control unit, I give it a signal to start. And when it starts, what it's going to do is it's going to sequence through a number of digital values here, and using those values, convert that to an analog signal to compare it to the unknown input. And when that process is done, it's going to signal that it has come up with an estimate. And the estimate is going to be the value, this digital value that I'm feeding to my D to A converter. And to drive it, because I'm doing this in successive steps, we call it successive approximation, I have to drive it with a clock. So let's consider, what does this D to A converter do? Okay, so coming back to my what I have is I have the following. I have get my notes here. So what I want is I want some sort of, so here's my digital to analog converter. Now you may think it's a little strange that we're using and I'm going to bounce back here. We have, and this is an analog, the entire system is an analog to digital converter, but we have to use a digital to analog converter to be able to come up with an estimate of our unknown analog input signal. And so the way we're going to do that is use this digital to analog converter. And first off, we'll talk conceptually what we want to do. So imagine now I have a system that looks like this. And I'm going to say my vref. So let's let vref we're going to say that's equal to 15 volts. And I have my two input signals, I have four input signals. This is going to be a 4-bit A to D. So this is A, B, C, D. And I'm going to generate an analog output. And so I could go through my truth table as follows. So here's my D, C, B, A. And if those are all 0, here's my V out. This would be 0. And if this is 0, 0, 1, this would be 1 volt. This would be 2 volts. And so on. And 1, 1, 1, 1 would be 15 volts. Okay, so this is what we're going to implement with our D to A converter. So what we want to do is we step through, we're going to generate some sort of analog output that is proportional to our binary count in. So the question is, well, how are we going to do that? So again, we draw on our handy dandy op-amp. And I'm going to ignore, because we're going to use this in a linear mode now. So here's my VN. And I'm going to, here's my minus and plus. And here's RF and RN. So here's I1 or IN, and here's I feedback, and here's V out. So we know that Zn is equal to infinity. And we have a virtual short. So if this is ground, if I have ground at this terminal is also considered ground, but no current flows into the op-amp. So I know the current that flows into a node has to equal the current that flows out by Kirchhoff's current law. So we know that IN is equal to VN divided by RN. And I know that IF, notice my direction, is equal to minus V out divided by RF. And those two are equal. So I know that IN is equal to IF. So we have VN over RN is equal to minus V out divided by R sub F. And my gain, which is equal to V out over VN minus RF over RN. And that should look familiar to all of you from your circuit analysis or maybe your electronics course. And so this is just basic op-amp operation. Okay, so you say, all right, well, that's great and wonderful, but how does that help us in our D-to-A converter? So what I'm going to do is I'm going to recall this drawing that I gave you up here, and I'm just going to scale my output voltage accordingly. But if I now have the following. So this is going to be V sub D, V sub C, V sub B, and V sub A. Now remember, these are digital signals, so they'll be either at 0 or some finite value. And I'm going to implement them in a configuration which we call a summer amplifier. So here's my R sub F, and this is, I'll make this 1 k ohm. And this will be 1 k ohm. And this is 2 k ohm. This is 4 k ohm. And this is 8 k ohm. And so if I apply my voltages, so I'm going to let V sub X is equal to 0 or 5 volts. I have a similar truth table as follows. So I have D, C, B, A, and 0, 0, 0, 0. And this is now, here's my V out. So this is 0. And this is minus 0.625, 0, 0, 1, 0, minus 1.25, minus 1.875, and so on. So now what you see is by using a summer amplifier, which now involves using just one op-amp and using, again, I need a number of resistors. So if I have a 10-bit A to D, then I need 10 input resistors, a feedback resistor, and so now I can implement this, and there is very fast response with my D to A converter. So we see that a D to A converter is a very straightforward process. What is a little bit more difficult is coming up with an analog to digital converter. So one thing that I might do is I might use maybe semiconductor switches to switch in these voltages, because what I'm going to do is I'm going to have to energize those and step through some values to be able to come up with an estimate. So let's come back to how this successive approximation A to D works. Okay, we have two different strategies. One is a very simple strategy. So one is when I present my unknown input signal, and I start off, I get a start signal from my whomever wishes my A to D to start, and I have a clock that's going to start. And what I do is I set this register to 0. So recall this is some value, and I can start at 0, and I'm going to count until this output of the D to A converter just slightly exceeds my input signal. When I see that my input signal, when I see that this output of the op-amp goes from high to low, then I know that my conversion is done and I've come up with an estimate of my input signal. And that is how I can do my end of conversion. So I'm going to make a note over here so that you will see this. So successive approximation, let's see if I can. Approximation. One is counting. So basically, register counts from 0. Until ADC, until op-amp comparator I'm not able to spell today here. Okay, so bouncing back over here, we see that this signal goes from high to low. Okay, so I want to come back to the table, and I apologize for the bouncing. So I see if I have a signal that's very, very small, it's not going to take very long to count from 0 up to the value of interest. Okay. However, let's say that my signal now is going to oscillate, and it starts off at a very low value, then it goes to a value that's very close to the max, which in this case, the max value is going to be, so I'm going to finish this in. Using those values that I provided, this is going to be minus 9.375. Okay? So let's say that my signal varies from approximately 1 volt to 9 volts. And I'm going to find that my conversion time, the time from when I start my estimate or my process to estimate the digital value, is going to vary. So the bad news is this has variable conversion time. Which may be very, very unattractive, may be undesirable. Okay, so this is a bad thing that we talk about. Okay, so we say, all right, well, how might I do it otherwise? And let's come back over here to our presentation. Oops, that's not what I want. I want PowerPoint. Okay, so Imagine now I'm going to use a different strategy. I say, okay, what I'm going to do is I'm going to start doing this digital conversion process using individual weights. So I'm going to start off with the most significant weight and compare it to my unknown signal. So if my reference signal, which I'm generating, is larger than the input signal, then I'll set that weight equal to 0. So then I go to the next weight and I say, is this one greater than my input signal? And I work from most significant to the least significant. And it is very much the same as what we're doing in this case. I start off with the heaviest weight and I say, is it heavier or lighter? And it's very much like when you go to, well, they don't use those at the doctor's offices nearly as much anymore. Everything is electronic. But what they do is they basically have a little slide there and they slide a weight, and basically they're trying to equalize the weight on this bar and the weight that you're basically putting on the mechanism so that you balance it out. In this case, what we're doing is we're starting with the heaviest weight and we're working our way all the way down to the smallest. So you say, well, that sounds a little more tedious, but the good news is when I do my successive approximation, the second approach would be bitwise. So we start with the most significant bit and work towards LSB. And so what we'll do is we'll continually add and remove weights so that our reference voltage is going to be just below the unknown voltage. The good thing about this is a constant conversion time. Okay? So because it's a constant conversion time, if it's a very small signal or if it's a very large signal, it doesn't matter because I'm going to start with the most significant and work to the least significant to basically come up with an estimate, a digital estimate of the actual value. So I'm going to try something here. I'm going to keep going to the wrong thing. So I want to annotate this, and let me see if I can, let's see, get out here. I don't have my keyboard, so I can, let's see, end show, and let's come over here, because I want to do an annotation for you here real quick. Too soon with the keyboard, excuse me. So what I have here is this is my unknown input signal. Okay, and this is a reference signal. So I'm generating a signal that I want to compare, and I'm generating that internally. And so when I have finished my digital value here, this is going to be the digital result. The last value that I have in that register is going to be the last value that will be my digital estimate of this unknown input signal. Okay, now we have one last issue to. Okay, so question here in terms of the successive approximation. Okay, so let me come back to this picture here. And so what happens is I'm going to, with the counting, I'm going to set this register to 0. In every clock cycle, I'm going to increment it by 1, just like I would with a counter or a timer. So this value is going to count from 0 to, in this case, FFFF, starting at 0 and then going to 1, 2, 3. So if my value is small, I will do my conversion very quickly because I'm just looking for one transition of high to low. Whereas if I do it bitwise, so let's say that I'm going to calculate a value. So this is 8 bits, so I have 255 possible values. So I'm going to count. My small value might take a couple clocks. My large value might take 255 clocks. Well, if I say, okay, let's do it a different way. Let's compare it first to the most significant and see which is heavier or lighter. If it's, and I'm thinking of the weights here, is that if my reference is bigger than my input, then I set that bit to 0. Then I do the next significant bit and I compare to my unknown input. Now the second question that comes in is this thing called an SHA. Okay, so imagine now, have any of you ever tried to take a picture of a dog or a small child and you want them, you see they have a real nice pose, but as soon as they see you with the camera, then they move. Okay, well, we have the same thing when we're trying to sample signals. Okay, so I'm going to, real life signals change with time. And let me fix this here. So because they change, what's going to happen is I have to basically do something to stabilize that signal. Just like if I had to try and take a picture of a child or a dog, I would like for somehow to be able to get them to hold still while I take the picture. If I was taking pictures 100 years ago where they had very slow shutter speeds, that's why people never smiled, because they had to stay still for a long period of time. But that's a little tangent. So what I need is I need a stable signal, because when I'm doing this conversion process, I would like this value to be steady. I don't want it to be changing while I'm trying to come up with some estimate of its value. So we need a way to keep the value constant. During the conversion process. And the conversion process is kind of slow relative to maybe some of the content of our signals. So what we do is we make a copy of the signal. So and the way we do that is as follows. So I'm going to basically have some sort of a switch conceptually. I have a resistor, and I'm going to, so here's my VN sample. So what happens is, here's my VN, which changes with time. And so what I'm going to do is, for some short duration, I have to charge up this capacitor. I'm going to, so I'll close the switch for some period of time. I'll charge the capacitor and then I'll open the switch, and while I'm doing the conversion process, this is going to be held steady. And so this is what is called a sample and hold amplifier. So we'll see that conceptually, this is how it's going to operate. When we say it's an amplifier, we say, well, this doesn't look like an amplifier to me. So what it is it's basically giving you a symbolic representation, and we call this a SHA. So when I come back over here, what I see is I'm basically bringing in my unknown voltage. I'm going to take a sample of it. Now this is going to be a sample of my input voltage, and I'm going to compare it to this reference to to come up with an estimate of a digital equivalent value that is an approximation of this analog signal. And the approximation part, or that part of that comment, is due to the fact that we have a quantization limit due to the number of bits that we're going to use to represent this value. So the more bits we have, the higher the resolution, so the smaller the quantization error, the better the approximation. And so with 10 bits, we have a reasonably good ability to be able to represent that signal. We have 1024 possibilities, including 0 to 1023, which is a reasonably good estimate of our system. So again, we live in an analog world, and we have to virtually anytime we want to use these analog signals, we have to go through a process to be able to convert them to digital signals so that we can then process them. And in classes like digital signal processing, you learn how to implement things like digital filters, how to do spectrum analysis, and how to do other sorts of things that you can do with these digital signals. If you look at two-dimensional, your cameras, then you do two-dimensional signal processing, and so on. And so the thing is this is the fundamental operation that we need to do to be able to bring in these analog signals so that we can actually use them in our kinds of applications. So what we're going to do next time is we see that this process has to all be configured, and we'll see that the actual implementation on our microcontroller, and I'm going to come back over here. In fact, let me go to this view because it's a better view. We'll see that we have one 10-bit analog to digital converter. We saw that we have 16 analog lines. We only have one analog to digital converter. So what we have to do is we have to do some pretty significant configuration to configure this analog to digital converter to use all 16 lines if we wish to use them. We may have certain strategies or needs for how we're going to do the conversions. Some might have to be fast, some might have to be slow. And so what we'll do is we'll see that we have a significant number of options, and more than we would go through in the remaining time of the lecture. So what we're doing today is just learning the fundamental concepts of what we need to do or how we need to use this analog to digital converter and how it works. So in our implementation, we have a successive approximation conversion. So we see it's going to take a certain number of bit times. It's got to take at least 10 clock cycles to do this conversion because we have 10 bits. And we'll see that actually it's going to take us 12 clock cycles to do a single conversion. We also have to worry about how fast is my analog to digital converter, and can it do it at what rate can it do those conversions? Do I have to slow down the peripheral bus or not? So we'll get into all those configuration details, and the last lab that I will do videos of will be showing you how to do the analog to digital converter. And then later on we'll talk about how we control motors as well. But with everything that we're covering in the class, I'm hoping that you'll start to recognize that you can do a tremendous amount of projects you can do a lot with what you have covered in this class, because you have covered all the fundamental interfaces, or will have covered all the fundamental interfaces and the issues that you would need to work in a real-world environment. Okay, so any questions on the analog to digital converter, the conversion process, a flash A to D, or the digital to analog converter? So I'll wait for any questions. Otherwise, that is our topics today. Okay, so on the tests, we have a test. The last one is the one that is graded. So both are not graded. We only grade one. You get a second attempt in case somehow you mess up the first one. But again, trying to give you as much flexibility as possible, recognizing that not everybody has high-speed access or reliable access and so on. So I'm just trying to make sure that nobody gets left dangling without being able to complete the test. Let's see, question, how do we know if your submission or written answers were recorded correctly? Well, you see on the screen what you have actually typed in, and so there should be no question as to what your input is. I've not seen any instances of where if you type in, so when you submit the test, it's a reliable system. There have not been any issues of somebody submitting something that's different, or they submitted and what they submitted is basically distorted. So I don't think there's any issues there. Other questions? Okay, well, thank you, everyone. I wish I could see you live, and look forward back to the days when we can all meet together live, and we'll continue this through the duration. If you have any